Everyone, I'm Tuan Tran. I'm from the LSD lab at the University of California, Santa Cruz. And today I will be talking to you about highly available, decentralized, publish-subscribe systems. This work was done in collaboration with my colleagues Haofan Zhang
Hi.
and Roy Chapman, and our advisor, Owen Arden. So a little refresher about publish-subscribe or pub-sub systems. Pub-sub is an approach to asynchronous messaging in distributed systems. And in these systems, publishers will register to a broker the types of events that they will produce. And subscribers will subscribe to the broker the types of events that they're interested in. And after registration and subscription, when a publisher publishes an event, it sends it to the broker who would then notify the corresponding subscribers that are interested in that event. Now, there are many interesting use cases for pub/sub, but one of these use cases is distributing revocation lists. In a distributed system, there are many participants. If one of these participants needs their credential to be revoked, the publisher sends the fingerprint of the revoked key to the broker, who would then notify the subscriber. Now, there are several challenges that needs to be solved for these revocation systems. The first is that these systems work fine as long as our publisher and broker are still functional. If the publisher goes down or it becomes malicious, the broker and the subscriber will not receive any notification, or they could even receive malicious notifications. Additionally, if the broker goes down, then the entire system also stops. Now, to save our kitty broker here, modern pub/sub systems will rely on replication for availability. Right? So replication allows the system to remain functional as long as the majority of the replicas are alive. But standard replication only scales to hundreds of nodes and requires centralized membership to manage the set of replicas. So to deal with this problem of availability, recent pub/sub systems integrate with permissionless ledgers to decentralize the broker and inherit the strong availability guarantee of these permissionless blockchains. In Ethereum, for instance, there are over 1 million validators, at least a third of which needs to fail to impact availability. Furthermore, it's permissionless, so it's completely public and anyone can join the network. However, we still have that problem of a single point of failure in the publisher. Right? But similar to earlier, we could probably rely on replication to increase the availability of our publisher. There's still the problem that if all the replicated nodes for the publisher comes from the same party or organization, we still have a single point of failure. Now, the second problem to this is we need to be able to authenticate the data, right? If we want to decentralize the publisher and allow anyone to become one, how can we trust them to publish authentic data? And furthermore, there's no reason that they will participate in our system because there's no incentive to compensate both the costs of making transactions on-chain and also their compute resources. The next challenge is that when integrating with a public ledger, the communication channels are also public. Right? So if the data being published is sensitive, we may want to protect the secrecy of this data. So these are not all of the problems. Let's consider a more concrete example of our revocation example. Suppose we're dealing with a credit card reward program that will reward customer points on-chain for each purchase that they make off-chain through a point-of-sale system. And customers can redeem these points on-chain for gifts and services. Now, in the event that the customer lost their card, to prevent further losses, the customer would want to first inform the on-chain points program to stop accepting redemption requests, and secondly, inform the off-chain point-of-sale system to stop accepting the card. So how do we make both on-chain and off-chain revocation effective and efficient? Right. So that example that we just saw involves both on-chain and off-chain subscribers. And existing works such as Trinity and HyperPubSub requires an off-chain subscriber to send an additional transaction to notify its on-chain component. Right? Such an approach is called monitor and react. Right? And this approach will cause a long delay for on-chain subscribers before they can react to these events. And it can be even worse when the network experiences congestion. So, how do we deal with all these challenges? Well, our solution in this work, we present a fully decentralized pub subsystem that addresses all of these issues. Right? So previous pub subsystems either rely on blockchains for availability but lacks confidentiality, or they rely on trusted execution environments for confidentiality but provides weak availability guarantees due to their standard approach to replication. So Decentagram combines both of these technologies into a highly available and confidential pub subsystem. Our smart contract framework can authenticate trusted execution environment, or T, components on-chain, eliminating the need for trust in publication. We also support on-chain notification. So Decentagram can be used in more realistic decentralized applications, or dApps, with both on-chain and off-chain components. Lastly, the system provides an incentive mechanism so any capable machine will be motivated to become a publisher to earn rewards. So to discuss more about the details of our system, here's Hao Fan.
So here's an overview of the Decentagram. Decentagram consists of several components, such as on-chain broker, as this part, which is a smart contract, and a number of publishers wants to publish events with messages, which is this part, and a number of on-chain subscribers, which are also smart contracts, and as well as off-chain brokers and subscribers, which are regular computer programs. To set up the components in Decentagram, we first deploy on-chain broker contract, and the publishers can now register with the on-chain brokers with message channels using a channel name. After the on-chain subscriber are deployed, they can subscribe to this message channel using the channel name. And similarly, the off-chain subscriber can also subscribe to the same channel using the same name. Once the notification channel has been set up, publishers can start to publish events. And now let's take a look at how they can publish events. Decentagram supports two approaches to authenticate events publications. If the source of the event is verifiable, such as digitally signed messages, the smart contract can authenticate the message directly. But if that's not the case, secure enclaves are needed to produce the publication data. And the smart contract will verify the authenticity of the enclave message by verifying the signature on the data and the enclave's certificate chain. The root of this certification is the CPU manufacturer's key. This ensures that this data is produced inside of an enclave. This authentication scheme fits for the data that can be fetched via a TLS connection or result produced directly from the enclave. Once the data is authenticated, the broker will be responsible for distributing the events to subscribers. So let's take a look at how on-chain subscribers get notifications. The on-chain subscribers are smart contracts and interested in some events. And when an event is published, the on-chain broker issues cross-contract calls to the on-chain subscribers, which will notify the subscribers within one transaction. So there's no delay comparing to the monitor and react approach. In addition to on-chain subscribers, Decentragram also support off-chain subscribers at the same time. And here's how they get notifications. Off-chain subscribers are regular programs running on various compute devices such as servers, PCs, laptops, and so on. When the on-chain brokers receive the on-chain event, receive the new event from the publisher, in addition to distributing the event to the on-chain subscriber, it will also emit an event within the same transaction. And that event containing all the details of the publications. The off-chain brokers will monitor these events in each blocks by continuously fetching blocks from the blockchain client. And once the event is found, it will notify their subscribers. This setup is completely decentralized because the off-chain broker only need to receive blocks from a blockchain client. So a blockchain node itself can be an off-chain broker by itself. Finally, we need to consider incentives. Since it's a decentralized system, the publisher needs incentives to motivate their publications and also compensate their cost. Previously, we showed that when on-chain subscribers are deployed, they subscribe to the on-chain broker using a channel name. And during this step, they will also include a deposit that's used to pay for the notification. When a publisher publishes the data, they are rewarded for each publications that sent to the subscriber. And this reward will be transferred from part of the deposit to the publisher. This setup allows multiple publishers to compete with each other, but only the first one will receive the reward. So this not only replicates publishers, but also incentivizes publisher replication. So far, we have shown how events are published and notified, but how do we ensure end-to-end encryption to preserve confidentiality? The publication event is a string of bytes, so we can simply encrypt this event. But the challenge is to distribute the encryption key to the subscriber. There are two ways in which the decryption key can be distributed. If the publisher and subscriber can communicate directly, they can perform a key exchange through a TLS connection. Otherwise, we present a decentralized key exchange protocol. First, the off-chain subscriber will be acting like a publishers that publish a key request event with its public key. And that event will be notified to the publisher, which is now acting as an off-chain subscriber. The publisher will receive this key through the key request event and authenticate the key. If the key requester is allowed to receive the event, the publisher will encrypt the notification key using this public key. And the encrypted notification key will be published to the blockchain via another event. And the option subscriber will receive this key through the new event. This approach is appropriate when both the publisher and the subscriber can be expected to protect the confidentiality of the data. To show the robustness of Decentagram, we conducted studies on the replication list distributions using Decentagram. Let's revisit the revocation list example from earlier. Here we have a typical scenario of revocation of keys. Each entity in the system holds their own private key. When one of them gets compromised, we will put its key fingerprint into the revocation list, so others will stop communicating with the compromised node. In a system consisting of different enclave components, the replicas of one type of enclave components can have the same enclave image hash, but each replica can have a unique public key pair. When a version of an enclave program are found to be vulnerable or even compromised, we want to revoke all enclave instances running that version of the enclave. In this case, we don't want to add individual keys into the revocation list because different replicas can have the same enclave program hash but different key. So what we want is a revocation scheme that not only works for regular keys but also works for enclave images. Decentagram smart contract framework supports 3 ways in which revocation can be done. The first approach is common in many BFT systems and some federated security systems. We assume the system has some federation of mutually distrustful people. They can express their agreement on revocation by casting vote to the smart contract. This allows voting to revoke both keys and enclave images. They can cast votes for keys they want to revoke, or they can cast votes for enclave images they want to revoke. But can we do something more advanced than voting so that we don't need human interventions in some scenarios where the evidence is concrete enough? The answer is yes. So imagine a private key is leaked or partially leaked. An auditor can demonstrate the proof of that key is leaked by signing a predefined image or using partial knowledge and enumerate through enough tries to end up signing with a predefined message. The smart contract can verify this signature of the message to determine that this key is leaked. In case of the enclave, a properly implemented enclave should never reveal its private key to the public. So when its private key is leaked, we could imply that the enclave program has vulnerabilities. By sending enclave certificate chain to the smart contract can determine that this enclave has vulnerability and add the enclave into the revocation list. And even better, with a way to verify signatures, we can even detect things such as conflicting messages. Suppose the components are running some leader-based replication protocol, and the leader sends the conflicting message to different replicas. Each message is signed based on 2 separate hashes. One denotes the sequence number, and another one denotes the value. When an auditor learns of these conflicting messages, they can send them right away to the smart contract. And since we are only comparing the hashes, the data confidentiality is still preserved. Now Tuan will give an evaluation of the Decentagram.
All right. So moving on to the evaluation. Our first evaluation considers the on-chain costs of our revocation example. We evaluated the 3 different types of revokers. And for the verification of just elliptic curve signatures, we see that the cost to deploy and report for the various revokers is around the same. In the case of enclaves, the enclave voting revoker costs around the same as the key revoker because we're just verifying signed votes. But for the conflicting messages and compromised keys, the cost to deploy is high because of the additional library contracts that are needed to be deployed to facilitate certificate verification. And the cost to report is high because we need to verify the entire certificate chain to revoke the enclave. Okay, in this next evaluation, we break down the gas costs for the various operations to show the limitation of on-chain subscription. Each block in a blockchain have a size limit. And in a blockchain like Ethereum, that limit is 30 million gas, as shown here on the bottom. And since our on-chain operations, such as subscriber notification, cost gas, this limits how many on-chain subscribers we can have. However, this limit of 30 million gas is more than sufficient for most applications because on-chain subscribers should contain only minimal but crucial application logic. For example, going back to the revocation example for credit card rewards points, a single on-chain subscriber is enough for the entire service, which can handle thousands of cards and point-of-sale machines. Our next evaluation looks at the throughput of block processing. Since events that are emitted by the smart contracts are included in receipts, we look at how the percentage of the receipts we process impacts the throughput. We evaluated 2 versions of our off-chain broker, one that resides inside the enclave and one that doesn't. For the non-enclave version, we see that the throughput drops as more receipts are processed, but hits a rate of around 80 blocks per second. Now, for the enclave version, we see the throughput drops even more drastically and eventually reaches 8 blocks per second. However, this is more than sufficient for most blockchains. For example, in Ethereum, the block arrival rate is 12 seconds per block. So at a rate of even 8 blocks per second, this is more than enough to process blocks faster than they arrive. We want to advertise that our code is publicly available in case you want to experiment with it. And our smart contract framework not only works on Ethereum, but has been tested on a variety of other EVM-based blockchain networks as well. All right, so to summarize, pub subsystems only provide a weak availability guarantee due to the limitation of the underlying permissioned replication protocol. And previous works that integrate with blockchains strengthen this availability guarantee, but introduces several challenges. In this work, we present Decentagram, the first fully decentralized pub subsystem that solves all of these challenges. And our system is the first to enable on-chain T authentication as well as on-chain notification. That is the end of our talk. Thank you for listening, and we'll take any questions from our YouTube audience.